All right. Now we need to make conclusion. Yeah. So we have a powerful tool. So this L'Hopital's rule is a powerful tool to help us do the comparison of two growth functions. Yeah. All right. So we can make conclusion. The algorithm with growth function n log n is faster than the one with growth function n squared. Yeah. By taking the ratio, yeah, we can see that. Okay. Yeah. Conclusion. That means our method number 2 is faster than our method number 1 for the element uniqueness problem. Yeah. Okay. All right. Yeah. Next, B.3, bubble sort. Our second sort. Yeah. Bubble sort. You learned before, right? Yeah. In your data structure class, yeah, CS3250, you learn this bubble sort. Yeah. Okay. But here, our understanding, we will use a higher level understanding. Yeah. Because at that time, in your data structure course, at that time, you just learn how to sort an array, right? Yeah, bubble sort. How to do the sorting. Yeah. Okay. Yeah. Here, our understanding, we will use the problem solving background to understand it. Yeah. All right. Yeah. Yeah. So we revisit our problem number 6, sort an array. Yeah. Yeah. So let's study a typical array with n elements. Yeah. Yeah. I remember I mentioned for this class, I plan to give you 6 different sorts. 6 different sorts. Yeah, this is our second one. Question, why we need to learn so many different sorts? So there are some good reasons. Yeah. Different sorts, they have different properties. Yeah. Sometimes you may need to use this property. Sometimes you need to use some other properties. Yeah. Yeah. Later you will see. Yeah. Under what situation one particular sort is better than the others. Yeah. Yeah. You need to look at your data. Yeah. If you need some special requirements for your data, then you need to select appropriate sort. Yeah. All right, so here, let's try to find a different property. Yeah. In order to get a different solution, you need to view your problem differently. Yeah. So here, we need to take a different angle to view the same problem. Yeah. All right, this time, let's consider 2 pairs. Yeah. Yeah. Given 2 pairs, we want to compare the values of these 2 pairs. Okay, yeah. Then, so there is a state, yeah, you know, out of order. Yeah. Yeah. Because if the elements are in order, they should be in ascending order, right? Ascending order, that's the final order we need for our data. Yeah. After the sorting, we want to see all the elements are in ascending order. Yeah. Then, we want to study a special state. So for that state, 2 elements are out of order. Not in the normal right ascending order. Yeah. In the reverse order. We want to study that special case. Yeah. All right. So here we consider some critical property. If the array is not sorted, all right, not sorted, we want to see what do we have? Okay. All right. There must be two adjacent elements that are out of order. Can you see the property? There must be two adjacent elements that are out of order. So why? Here you can use contrapositive method. Yeah. Still in our discrete math, okay? In discrete math, the logic part. Yeah. Logic part. Yeah. There is a method called a contrapositive method. Okay? Here we use the contrapositive argument to see this property. To see this property. Yeah. So we do this way. Yeah. Why the statement is correct? Yeah. All right. There must be two adjacent elements that are out of order. If the conclusion is incorrect, contrapositive, we want to negate the conclusion. Yeah. We have hypothesis and a conclusion. This is hypothesis. If part, hypothesis, then conclusion. Yeah. All right. Contrapositive, we negate the conclusion first. Okay? All right. Then we want to get a contradiction to the hypothesis. That's the contrapositive method. All right. Negate conclusion. There must be two adjacent elements. Okay. Then no two adjacent elements are out of order. That means when you look at any two adjacent elements, they are in order. Okay? Any two adjacent elements, they are in order. You cannot find any pair of adjacent elements that are out of order. No such pair. No such out of order pair you can find. Okay? That's the conclusion. But now, that's the negation of the conclusion, right? Negation. We negate it. Okay? We negate it. Yeah. So no out of order adjacent pair. That means all adjacent pair are in order. Then it must be in ascending order, right? Yeah, because you keep going up. Okay? You're never going down. You keep going up. Okay? Yeah. Then increasing order, ascending order. Yeah. All right. So then your array is ordered. Then you get a contradiction to the hypothesis, right? Hypothesis tells us array is not sorted. But we get a contradiction. What do we get? Array is sorted. Yeah. Then it tells us our negation of the conclusion is wrong, right? Negation of the conclusion is wrong, so the original conclusion is correct. Okay? So this statement is correct. Yeah. So we use the contrapositive method, we can see this statement is correct. Yeah. Then this statement is useful to give us the insight to solve this problem. Insight. Solving this problem. Yeah. All right. Yeah. All right. So then we need to introduce a new concept, this concept called inversion concept. Inversion. So what is the inversion? This out of order thing, it's an inversion. But we need to use the, some rigorous way to represent this concept. Yeah. A pair of elements. Here, not necessarily adjacent. Yeah, we do not need to require two adjacent elements here. Yeah. Any two elements in the array, AI, AJ, yeah, is called an inversion. Then we need these two conditions. First, I subscript is less than J subscript. Yeah. But the value of the elements, AI value is greater than AJ value. The opposite order. Yeah. So then if you find a pair like this, you call it inversion. So this is an inversion of the array. Okay? Yeah. All right. If we use the inversion concept, then we can modify our previous statement like this. If the array is not sorted, there must be an inversion, right? Yeah. There must be an inversion, okay? Otherwise, we can use contrapositive argument to prove it's correct. Otherwise, if there is no inversion, right? No inversion, then any two adjacent elements must be in order, so that all the elements are in order. Okay? Yeah. So we get contradiction to the hypothesis. Yeah. The whole array is sorted contradicts the hypothesis part. Okay? Yeah. So yeah. So we have this. Yeah. But in order to do the sorting based on this property, we want to write our sorting algorithm. So we want to improve. We want to, although we still use this property, but we want to use a different version. This newer version is more friendly for our coding, more friendly. So what's that? More friendly. Okay? All right. There must be an adjacent inversion. We change inversion to adjacent inversion because that's enough. Yeah. If no adjacent inversion, yeah, there must be an adjacent inversion. If no adjacent inversion, yeah, so we know. Yeah. Yeah. If there is any inversion, then sooner or later you will get an adjacent inversion. Otherwise, if any two adjacent elements, no inversion, then ascending order, right? If you look at any two adjacent elements, no inversion, then it must be in ascending order. Okay? Yeah. Yeah. All right. And this second statement is more programming friendly. Programming friendly. Why? Because when we work on adjacent inversion, we can do less work. Okay? We only need to do adjacent comparisons. We do not need to do non-adjacent comparisons. Then it's much easier. Okay? So this second version, yeah, more friendly for our programming. Yeah. Okay? All right. Now, yeah. So here you can see, yeah, the second statement we use the local view. Adjacent, it's a local property, right? Yeah. The first statement we use the global view because we can have a global inversion in the first statement. Okay? Yeah. So here you can see in our problem solving of computing problems, one way to make the problem easier, we do conversion from global view to local view. We can make our problem easier. Yeah. All right. Yeah. Now, how to fix the inversion problem in a given array? Yeah. So now our understanding based on the inversion property in a given array. Yeah. So the question is, given an array, if it is not sorted, then there must be some inversions. The question is, if we can find an inversion, then we fix that inversion. We change the order of the two elements in that inversion, then that inversion is gone. Okay? So if we can remove all the possible inversions in a given array, then when we get arrays sorted. That's the idea of our new sorting algorithm. Okay, all right. So let's implement this implementation idea. Yeah. Remove all the local inversions by local swaps. Yeah. When you see one inversion, you just swap two elements in the inversion, then you remove that inversion. Okay, that inversion is gone. Okay, then you can move to the next inversion. Then you make another swap to remove it, and so on. Yeah. And your goal, you want to remove all the possible inversions in a given array. Then you are done. Okay? Yeah. So that idea, that implementation idea. Okay. All right. Yeah. So let's write the detailed steps. Yeah. The first step, start from the first element for each scan. You need to scan the given array multiple rounds from beginning to end, several rounds. Okay. Yeah. Yeah. So each round you start from the first element. Yeah. Then, first you need to find an inversion, then do a swap operation to remove it, then go to the next adjacent pairs. One by one adjacent pairs to do the checking and a possible swap, then next round. Okay. Second step, do swaps one by one from left to right if necessary. Yeah. Only when you find an inversion, then you do a swap. Otherwise, you keep moving. Yeah. All right. Step 3, start at the first in-place element. Still remember the in-place concept we defined before in that selection sort problem. Yeah. We learned this in-place concept. Yeah. An element, if we call it in-place, that means it is already in its destination location when the array is sorted. Okay? It's in the right place. Yeah. What is the right place? Yeah. When the array is sorted, the location of this element is its right place. Okay? Yeah. Yeah. All right. In each scan, so here, when we implement the swap, checking, swapping, this kind of operations, there is one property, and there is one basic property you need to observe each round. Yeah. All right. Let's look at one round. Okay. The first round. Let's look at one round. Yeah. In one round, do this. Every time you check two adjacent pairs. Yeah. Checking possible swap. All right. Yeah. Think about after you complete one scan. Can you see if there is any element in place after your one scan round? Any element is in place? No. Okay. Swap, checking, possible swap. Okay. From beginning to end. After you reach the end, can you see which element is in place? Okay. Yeah. Look at the maximum element in this array. Okay. Suppose here you look at the maximum, largest element in the array. Yeah. So you keep track of the largest element in the array, because largest element is always greater than its next element, right? So you need a swap. After that swap, then you do next adjacent comparison. The largest element is still greater than the next one, right? Yeah. Every swap your largest element, you always move it one position to the right. Okay? When you hit the end, the largest element should be the last one, right? Yeah? So after one scan, the largest element is placed at the end. That is in place. Because largest element is supposed to be at the end of the array, right? That is in place. That means every time when you do one scan, you put the largest element in place. Okay? That's one round. But the next round, don't touch that element already in place. The element already in place, why you touch it? Okay? So the second round, you only need to do the comparison with the second, the second to last element. Yeah. The last element you should cut off. You don't need to touch that. Elimination. You can eliminate it from the consideration. Okay? So you reduce your array size by 1. Okay? Reduce your array size by 1. Yeah. Then another second largest element you put in place. Yeah? Because this kind of, swap. Yeah. The second element in place. Then you chop it off, reduce the size by another one, and so on. Every time you put one element in place, and you reduce the problem size by 1. Yeah. At the end, you get a whole array sorted. Yeah. So that's the properties, implementation, steps of this algorithm. Yeah. All right. Now, there is one element in place for every scan. The in-place element of each scan appears at the end of the current array. The basic properties of this algorithm. Yeah. The current array is a subarray that excludes all the in-place elements. Current array. Yeah. You make it smaller, smaller, smaller. Yeah. All right. Yeah. All right. So the visual imagination. So after you complete the whole sorting in this way, visual understanding. Yeah. The swap looks like a bubble moving to the right. Yeah. Adjacent. Yeah. So it's a small bubble. Okay. Moving to the right. Yeah. So we call it a bubble sort. Yeah. Yeah. All right. Then efficiency, because now you need to count the number of comparisons. Number of comparisons. All right. Efficiency analysis is similar to that of the selection sort. You do round by round. Yeah. Every time, every round, you need to do certain number of comparisons. Yeah. The same number as you did in the selection sort. Yeah. So here we do not repeat it. Yeah. So we use the same formula as the selection sort. Yeah. All right. Last question. What is the basic operation? Use our definition of the basic operation. Here we have two operations. Comparison operation and swap operation. Yeah. Now you compare these two operations. Which one contributes more to the running time? Comparison or swap contributes more to the final running time. Can you see a little bit? Which operation you need to do more? The number of times, more times. You need to do more comparisons or more swaps. That question. Can you see the difference? Correct. Correct. Every time when you look at two other JSON elements, you need to do one comparison, right? But you may not need to do swap. If they are in order, you don't do swap. Okay? Only when they are out of order, you do one swap. Okay? Think about when the given array is already sorted, then no swap, right? But you still need to do the same number of comparisons. Okay? Even the given array is sorted, you still need to do the same number of comparisons. Even if it is sorted. Yeah. Okay? Yeah. Then some students may ask this question. If the array is sorted, why you still need to do the redundant comparisons? Right? Yeah. Yeah. I don't know if any of you may ask this question, but here I just, if any of you ask this question, yeah, let me answer here. Because the computer does not have eyes. Where your data is sorted, how does the computer know it, right? The computer does not know it, okay? Yeah, you feed the data is already in order. The computer is blind, okay? The computer just execute the instructions in your programs, right? Yeah, because you write the program in that way, okay? Yeah. If you want to make your some people want to, try to reduce the amount of work. Yeah. Then you need to do the checking, okay? You need to do some checking work. Then the computer knows, oh, the array is in order. But how much work you need to do for the checking, right? Yeah. If you need to do too much work for the checking, not worth it. Okay? Not worth it. Yeah. Yeah. So computer doing things differently as human. Okay. Yeah. So we have eyes, we can see, yeah, if it's ordered. So why do the redundant work? Yeah. Computer works differently. Okay? All right. Yeah. So we finished this topic. Yeah. Next topic, B.4, string matching problem. Yeah. So here we want to apply the brute force method to solve this basic string matching problem. String matching problem, so it's a basic application in real world. When you do the search, you do string matching problem, right? You do keywords based search. Think about that. Yeah. Yeah. Every day, many people, they need to do keywords based search. Yeah. How to implement the algorithm? String matching problem. All right, let's look at the question. Yeah. But in this topic, we want to understand one aspect in problem solving. That is the mathematical representation. Yeah. Okay, all right. Problem A, string matching. Yeah. Given a string of n characters, we call it text. Yeah. A block of text, okay? It's a long string. You can treat it as a long string, a block of text. Yeah. N characters. And a string of m characters, relatively short string with m characters, we call a pattern. Yeah. The keyword part, the pattern. Okay? Yeah. So then we do comparisons. Yeah. All right. Then, the question, we need to find a substring of the text that matches the pattern. Yeah. Substring anywhere in the given text that matches character by character to the given pattern. That's the question. Okay? Yeah. So it's a simple question. Yeah. Yeah. And we need to, the function should return its location. Yeah. The location of the substring. Yeah. So what do you mean? So what is the definition of the location? Yeah. The location of the first character of that substring. We use that index number as the location, the index of that character of the first character in that substring. Yeah. That location. Okay, all right. Leftmost, yeah. All right, yeah, the first solution. Yeah, yeah, so here we do the brute force method. Okay, straightforward brute force method. Yeah. There is an advanced solution in our textbook. Yeah, advanced, but very complicated. Very complicated, very hard to understand. Yeah, but in our textbook, okay? Yeah. So when you have more time, yeah, so probably after this semester, yeah, when you have more time, you can read details of that algorithm. Yeah. Yeah. Advanced stream matching problem, the solution. Yeah. All right. Here, straightforward thinking. Yeah. So let us write the mathematical representation of this question. Yeah. All right. Yeah. Text part. Text. Yeah. A sequence of characters. Yeah. So array of characters. Right? Yeah. Here we use T0, little t, T little t1, subscripts. Subscripts represent the locations of these characters. Yeah. All right. Pattern, yeah. Another array of characters. Yeah. We use little p. So P0, P1, Pn minus 1. Yeah. These two arrays of characters. Yeah. Then matching. We need to describe the matching condition. All right. Requirement. Find a location I such that, yeah, suppose we find a matching place. We want to describe, we want to use formulas to describe the matching condition. Yeah. Starting from location I, we have the first character matched. The first matched character T sub I equals P sub 0. Okay. First, match the character. Then, yeah, following the natural order from these two arrays, yeah, 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 yeah. The next character should also match. Okay, yeah. Then, if we T array, we move J position to the right, and the P array, we should move the same number of positions to the right, J to the right. That's the general expression. Yeah. Then the last one, T sub I plus n minus 1 equals P sub n minus 1. If all these equalities are satisfied, then we find one match. That's the algorithm. Okay? Yeah. Very simple. Yeah. Yeah. Straightforward. Yeah. But definitely not the best one. Not the fastest one. Yeah. And in our textbook, yeah, in that more advanced algorithm, yeah, the basic idea is try to skip as many characters as possible, because sometimes you do, when you detect some special condition, you can skip several characters. You don't need to do comparison. Yeah. So that algorithm try to explore all those cases that you can skip multiple positions. That's why that algorithm is very sophisticated. Because you need to consider all the possible cases that you can skip a few characters. Yeah, very sophisticated. Yeah. All right. Here, because if we do not skip, now it's pretty easy. Yeah. So not that hard. Okay. Yeah. All right. But the next, we want to fix the implementation details. Yeah. The condition. It looks pretty simple, yeah. But now we need to consider writing the code. When we write a code, yeah, we use nested for loops to do the checking, right? Yeah. Outer for loop, we need to cover all the possible substrings. Inner for loop, then we need to do comparisons here. Yeah. If one of the equalities is not true, we can move to the next substring. Okay? Next substring until we can find one substring such that all the inequalities are satisfied. Then we return the I number, the subscript I number. Yeah. All right. But we need to, when you write this nested for loops, you need to fix some detailed information. Yeah. Here, let's look at what important information we need to figure out before we can write this nested for loop. Yeah. All right. Yeah. Strategy, guess and verify strategy. Here I want to introduce a commonly used problem-solving strategy. Guess and verify. Make a guess. Yeah. Many times you need to make a guess. But your guess may not be correct. Yeah. May not be correct. Yeah. So you have to verify your guess and see if it is correct. Okay. If it's incorrect, you need to fix it. Yeah. Okay? Yeah, so here I want to show you how to apply this basic strategy to solve this simple problem. Yeah. All right. Let me draw a diagram. Yeah. Here, as a brute force, this is brute force method. As a brute force implementation, we need to exhaust all the M strings. So we define a M substring. A substring with M characters, with length N, we call this M string. Okay? Yeah. So we want to find all the possible M substrings in a given array. Yeah. Because that number is useful in our for loop. Okay? How many iterations do we need to do, right? Yeah. In our outer for loop, how many iterations we need to do? This number, the same number, the total number of M substrings, this many iterations in our outer loop. Okay, all right, yeah. Every time we extract M string from the text with consecutive characters, yeah. So consecutive M characters. Then we can do comparisons in the inner for loop. Okay, all right, yeah. Compare it with a pattern for a possible match. Yeah. All right, question, all right. Yeah. Here, let me draw a line segment to represent the text part. So this is text part. Yeah. One long line segment. Now, we know the pattern is much shorter. The pattern. Suppose this is the pattern. Okay? Yeah. The first pattern in the given text. Then the second pattern, we move one position to the right. The second pattern. Okay? The third pattern, another one character to the right, shift, move, like that. Okay. Keep going. The last pattern is like that. Last pattern. The question. Text has N characters, pattern has M characters. Can you use M and N to give me a guess? You need to make a guess. to tell me how many M substrings can you find here using M and N. How many different M substrings? Make a guess. In problem solving, we need to make guess. Many times, we need to make a guess. Yeah. Good. She knows plus that one. Yeah. But yeah, she knows plus that one. But many students, yeah, usually because they use their intuition. Yeah, yeah, yeah. When they make guess, you most of the time use intuition, not logic. Okay, not logic, intuition. Okay, using intuition. Yeah. So many students usually give N minus M by intuition. Right? Yeah. All right. So so that's the most common guess. Yeah, without using logic, but if you make that guess, N minus M, you need to verify it. Okay? You need to verify it. Yeah. The next question, how to verify it? Okay? When we do the verification, we need to use a special case, very special case to do verification. Okay? Yeah. All right. So how special? The one extremo special case, that is N equals M. Is it legal? It's a legal data, right? M and N happen to be the same. In that case, your answer should be 1, right? The whole text part is the same M substring, so your answer is 1. But if you make this guess, you get a 0. It's different from that special case answer 1. That means you need to make an adjustment, all right? So you need to add 1 back to your guess. Yeah, your guess very close, but still 1 short. Right answer. So you need to add 1 back to your answer. Yeah, yeah. That's the verify part. Yeah. So after verification, you can modify your answer. M minus M plus 1. Yeah, yeah, yeah. All right. The reason you got your correct answer the first round, you must have some experience before. Okay? When you do the counting, you have some old experience. Yeah. She has some old experience. She knows to do this, plus 1, this little thing. You need to do this. Yeah. Yeah. But most students, when they do not have experience, okay, you make your guess based on your intuition in your mind. Okay, yeah. So here, yeah, I want to introduce this effective strategy. Yeah. Guess and verify. Yeah. All right. Yeah. Let's continue. Yeah. Implementation details. Now, we need to write our nested for loop. Yeah. So here we know we need that many iterations, but still not enough. We need more details information to help us write our nested for loop in the implementation code. Yeah. All right. Our first substring. Yeah. It's very easy. So our first iteration, yeah, we need to take this substring. Yeah. But the question, what is our last iteration? What is the location of our last iteration? We need to also figure out, right? Yeah. So for the first iteration, our I equals 0. Our counting variable I equals 0. Yeah. But when we hit the last iteration, what is the corresponding I value, right? Yeah, because we want to know our for loop, the condition. When we write the condition in the for loop, we need to know the last I number. Last I number, right? Yeah, here. Yeah, last M substring But what is the I number in this question mark place? We need to calculate it, right? Yeah. So here, some of you, if you have experience, you can figure it out. Yeah, some students, because they had some training before, so they can use the experience to figure that out. If not, here, let me give you some method in problem solving. The method, I talked about it in our first lecture. Remember? First lecture, the chessboard question. We apply that important concept, invariance concept. Remember, invariance concept we used in our first lecture in the chessboard question. Here we need to use that invariance concept here. Okay? All right. How to figure out the subscript number here? We use the invariance idea. All right. Here we do this. Remember, we need to keep moving the M substring, right? We need to keep moving the M substring. When we keep moving, when we go through dot, we may get lost, right? The question, how do we keep track of our data when we skip many inside iterations? How do we keep track of data? In our first lecture, we know we can use the invariance concept to help us keep track of the data. Here, we need to discover that invariance. When we move M substrings anywhere within the range, can you see some quantity never changes? Is there any quantity never changes when you move your substrings? When you move your substrings, some special number never changes. Never changes. That number is important. Okay? Use your intuition. Look at it visually. Yeah? Something never changes. How about the length of the substrate? When you move, the length of substrate never changes, right? It's M, right? The length of the substrate never changes. You can use that as the invariance. Use that property to keep track of your data. So that length, although the length never changes, but you may like to use another slightly different quantity for convenience. The difference of n subscript and two n subscripts of that subscript. That's close to the length, right? One difference. But still never changes, right? So the difference of two n subscript. Beginning subscript, end subscript, take the difference. Never changes, right? So that's the invariance property. Okay. Now let's use this invariance to help us fix this question mark number. All right. Let's set up equation. That difference is n minus 1. All right. Then the last one, this question mark unknown, we use x to represent the unknown number. Okay? The difference, the subscript of the last character n minus 1 minus x should be equal to n minus 1. Right? It never changes. The difference never changes. So we set up equations. This is our equation. So we solve it for x. X equals n minus n. Okay? X equals n minus n. When you write the for loop, now you know your last I is this number. Okay? You do iterations so from I to this n minus 1 number. All right? So here we review our invariance concept. In problem solving, how do we use some special invariance property to help us keep track of the data. Okay, so you see another example, very simple example, but very useful in problem solving. Okay, yeah. So in this simple question, so you learned two important knowledge points. One is the strategy, guess and verify strategy. Second, apply this invariance property to keep track of your data. Okay? All right? Yeah. All right, so let me try to conclude the, the analysis part, pretty easy. Okay? The best case efficiency, when you look at the first M substring, you get a match. That's the best case. Yeah. So you do M character comparisons. Yeah. You do one substring comparison, but you do M character. This M number corresponds to the character comparison. Okay, comparisons, number. Worst case efficiencies, then you do M times the number of M substrings, yeah, N minus M plus 1. This many character comparisons. Okay, yeah. Average case, yeah, because from best case, worst case, all the other cases distributed evenly in the middle or linearly. Yeah, so I should use the linearly. Yeah, okay, yeah. So in that case, yeah. So here, let me draw a diagram. Okay, the best case. This is best case. M comparisons. All right, this is the worst case. Yeah, that number, M times, and all the other case normal comparisons distributed linearly between, okay? Yeah. But linearly here will mean 2M, 3M, okay? Linearly, okay? Yeah. Yeah. Between them. Right? Yeah. So if your cases are distributed linearly between worst case, best case, worst case, like that, okay? All right. Then your average case is our usual average. These two numbers adding together divided by 2. Okay? Yeah. If not distributed linearly in the middle, we cannot divide it by 2. Yeah. We cannot divide it by 2. Okay? Yeah. Yeah. Not in a linear way. So here, linear way. Because when we learn binary search, those cases not distributed linearly. Okay, the case is not distributed, so you cannot take average like this kind of average. When we go to the binary search, that case. Okay, all right, yeah. So we finish part B. Okay, all right. So part C, yeah, let's do part C Wednesday. Yeah, so we only have a few minutes left. But the one thing I want to remind you, after today's class, you will have first assignment, homework assignment number 1. Okay, so I set the starting time of this assignment, July the 1st. 12 a.m. Okay, yeah, 12 a.m. July the 1st. Yeah, that's so you can see the assignment posted. Yeah, then you have 12 days to complete it. July 12th. Okay, the last minute of July 12th. That's the deadline. Okay.